Okay, nice job. Diagrams sheet corresponds to which rule we read about yesterday? Raise your hand, 10 points.
Ooh, what's that guy? Does his name start with an H?
Raise your hand. Hund's rule, yes, that is correct. So Hund's rule basically says that you are going to distribute the electrons to where they are balanced, right? So symmetry. So if we look at this right here, the first thing we want to do is find the atomic number for all the elements. So on the periodic table, I found the atomic number. Hydrogen's 3, lithium, correction, hydrogen's 1, lithium 3, sodium 11, so forth, to rubidium. So I told you at the beginning of the period that this is like busy work, and then I could teach a kindergarten to do this. So the first one, we're going to place the arrow upward. What does that mean, the arrow is going up?
It's the way the electron's going.
Right, so it could be a clockwise direction for the electron to orbit around. Remember, they're following circular origins around the nucleus. They're all of them doing it. All the electrons follow circular origins. They just do it in different spaces. That's what the whole point of the shapes are, is to find out which space the circular origin is going into. Right, Claire?
Yep.
All right, so this is going, let's say, clockwise, and this is going counterclockwise. Make sense? And we go clockwise. So we go clock, counterclock, clock, counterclock, clock, clock, clock. So that's Hund's rule. It's a balance thing. So this is like the x-axis, the y-axis, and the z-axis. Well, we're going to get to them. I've only placed 1, 2, 3, 4, 5, 6, 7, and there are 11 to place. But I'm trying to show you Hund's rule. Hund's rule states that they will distribute x, y, and z for symmetry and balance purposes.
The John Green dude or his brother?
Yeah, he is.
For the elements concerns getting to the noble gas electron configurations. A fluorine wants to become 2p6. And how's it going to do that? Sophia? How's fluorine going to become 2p6? Anybody know?
He's going to take in another electron?
Yeah, it has to gain an electron. Very good, Cody. Points for you. So here we have fluorine as an element. Here's the electron configuration as an element. This is what it looks like from the Lewis dot structure. We have this single electron here. It wants to bond with, or get another electron. This is called a radical, and radicals are aggressive. Fluorine is the most aggressive nonmetal. All chemical reactions occur because of the nonmetals. It's like bleach. You have to have a desire. You can't coach desire. Remember that if you ever become a coach and you're trying to help kids win. You can't coach desire. So fluorine, it has the desire. It's going to aggressively go after and find another electron. And when it does that, it's going to behave like neon. So it's going to then be stable. So let's draw that configuration. Right, so when we write the configuration for the ion, you have to put the charge. It has gain of 1 negative charge.
Got it.
Alright, so when we're doing the electron configurations for the transition metals, you have to find the table of the oxidation states. So you can see for scandium, Sc, you have common at 3+. Sometimes you can get a 2+. Let's look at chromium. You've got common at 2+, 3+, and 6+. Iron, 2+, 3+, 4+, 6+, and 7. Correction, I was looking at manganese. Was that common? Manganese is very common, whereas iron is just 2+ and 3+. Cobalt, 2+, 3+, so forth. So these are the first row transition oxidation states. You have to look those up. You don't have to memorize those. That's why it's in a table. Any question on that?
The energy level N can be determined based on the periodic table, simply by looking at the row number in which the element is in. However, there is an exception for the D block in F1, in which the energy level N of the D block is N1, N-1, and for the F block is N-2.
Okay, very good. So what does the N correspond to? Right, energy level. How many energy levels are there? 7. Right, so the formula for the transition metal oxidation state, we have ns0ndx or ns1ndx. So those are the two possibilities. When it goes to oxidation state, you're not going to see ns2. That's the point they're trying to make to you here. So you're going to lose an electron from the S shell. Everybody clear?
This only applies to the first row transition metals. Adjustments will be necessary when writing the electron configuration for the other rows of transition metals. The noble gasket for the first row of transition metals would be the...
We're going to go over that. This right here, the orbital diagrams, we'll go over that first.
I get both.
Yeah, that's pretty simple.
What we supposed to do? What we supposed to do both sides?
Yes.
Okay.
Nice job.
I've got to lose both.
No, you're supposed to do both
Is
sides.
this right, Mr. Senator? Will you look real quick?
That is correct. Very good. So pick somebody to do aluminum. Configurations. There are 3 rules, the electron configurations. Which rule does the orbital diagram associate with? Raise your hand. 10 points. Yesterday in the book, we read about the 3 rules associated with electron configuration. The orbital diagram specifically addresses one of them.
So there's not allowed to be like 2 electrons there?
Right? They even gave you a visual picture of it. I said if you didn't read very well or understand what you read, you can look at the picture. 5 points starts with the H. Raise your hand. Christian? Hund's rule. Page 157 shows you an example of Hund's rule right here. And if you notice, the arrows are associated with what we see up here for the orbital diagrams. It's the same thing, Hund's rule. Fantastic. I know points, 5 points. If you can tell me what the arrow going up represents. All right, go ahead, Michaela.
Does it say forward slashes?
What does that mean? Anybody else? All right, TT.
One electron.
Okay, but what does the upward arrow mean, Kaya?
An orbital with 1 electron in the box. Oh wait, no.
Close. Austin? What? No.
It just says that it represents an orbital with 1 electron.
Right, but it's going in the upward direction represents a clockwise movement, and or an opposite movement, and then the downwind represents counterclockwise. So remember, we talked about since the beginning of this discussion that the electrons orbit in circular origins. They're following circular paths. They're not doing all sorts of crazy movements. They're following circular origins. They're moving as a wave, following a circular origin. So if I have a circular origin, right, the wave is going to follow that circular origin. Right? I don't do the wave very well, but that's pretty good on a circular origin. Right? And the orbital shapes just help us define where that wave might be. That's the goal. Everybody clear? Figure out where those waves are, where those electrons are moving. So this would be clockwise, counterclockwise. Clockwise, see what I'm saying? That's defining the movement there. Now if we look at sodium, it has 11 electrons to place. So we go 1 up, 1 down, 1 up, 1 down, right? Second one, energy shell. Now when we get to the P, remember the P's? You have to separate them. That was Hund's rule. They're going to disperse, so they're balanced, because balance is the nature of stability. You're stable if you're balanced. Then you go back to down, 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 then you have your last S where it goes up. Is everybody clear? Now we just want to draw your attention to one more thing in the book, page 156. You'll notice which orbital type, which shape type has the highest energy level. The P. Does everybody see that? That means those electrons have the highest frequency at the 7p. They're moving very fast, very energetic. If you hit something with that, it is going to react very easily. The p orbitals have the greatest desire. There's an old saying, you can't coach desire. You have to come in with it. You really have to want to be a part of the winning team. That's what really the non-metals are all about. They come in with the desire.
And how much was your
Okay, nice job. Pick somebody now. When you're writing the configurations, you're never going to see numbers higher than the maximum electrons that can be placed in the overall shapes. So over here, when we're doing the configurations for sodium, you don't need to write 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. Now you can do that, but the teacher's going to wonder why you're writing all that. That's a lot of work. You can just write 2p6. Because sodium has the structure for all those elements within it. If you peer into neon, you're going to see hydrogen structure. The electrons are going to move in a similar path. So elements build on what's already working. That's called confidence. Neon's confidence rests in hydrogen's structure. Fluorine's confidence rests in carbon structure. This is how the elements are so stable. If this wasn't the case, you wouldn't see all the elements to 82 being stable. There are a lot of reasons for that stability. The electron shell protects the nucleus and allows it to be stable. You remove the electrons and obviously you're going to have a big effect on stability. It's going to make sodium unstable. It wants to get rid of this electron so it can behave like neon. Its goal is to donate that electron. If you drop sodium in water, what will it do? Anybody know? It'll explode. If you drop a large enough piece of sodium in water, it blows up. Yeah, big explosion. So this wants to leave. Now it has to be in the close environment to an element that wants to take it, has a desire for it. So if you store sodium in oil, it will not react. But if you store sodium in water, it's going to react. It's going to lose this electron. Now when it does that, there's a configuration we can... This is sodium as an element. This is sodium as an ion. What? Well, the goal is to be like the noble elements. Like neon is a noble gas. All the elements want to behave in this stable configuration. So they're either going to lose electrons or they're going to gain electrons. Now the non-metals are like women, so that's how I remember it, and they want to gain. And the metals are like men, they want to lose. So this is a metal, sodium. It's going to lose an electron, this one right here, and it's going to form a positive ion because the proton in the nucleus is positive. When it loses an electron, which is negative, the protons give it that charge. So this is based on the charge of the nucleus. Balance. You have to find a data table, Lily. A data table. You have to go to the book or the internet and do a little research on them. You can't just assume what the charge is going to be because if you look on the table, right here, Lily, table.
Yep,
Gave it to you when you came in.
I'm looking at it.
No, the other one, other page. You'll see that iron has a 2 positive or a 3 positive. The most, I guess you would say, oxidation states would be manganese with 2 positive, 3 positive, 4 positive, 6 positive, and 7 positive. So you have to then investigate what to determine what the charge is going to be. What's going to determine whether manganese is 7 positive or 2 positive? Anybody know?
No.
Yeah. What's going to determine whether manganese is 7 positive or 2 positive? The nonmetals. That's why the nonmetals have such power in the periodic table, because they will come in and determine how many electrons are going to be taken. Because the nonmetal is the one that's taking them. Oxygen is not a share. Metals do not share electrons with nonmetals. It is called a transfer. So the metal is losing it. Look up here. Sodium doesn't want this electron. It wants to lose it. So they call it a transfer. It's not a trade. It's not a share. It's a transfer. It is transferring it to the nonmetal because chlorine has 7. It says, I have 7. Oh, you have 1. 7 and 1 makes 8. So then chlorine is no longer going to behave like its configuration. It's going to behave like the noble gas that follows it. I don't have that memorized, but if you look on the periodic table, you can see the noble gas that follows chlorine, which is argon. So when chlorine gains that electron from sodium, it now behaves like argon. Any question on that?
Transition metals. The noble gas before the first row of transition.
Your second career going out.
Alright, check yourself.
Is this right, Mr. Steinecker?
It is correct.
Can I do aluminum too?
No, you pick somebody to do aluminum. Don't pick me.
Why didn't you pick me, Jimmy?
Because she had her hand raised.
No, it would be too.
Alright, very good. Nice job. Step 1, when you're doing orbital diagrams, go to the periodic table, find the atomic number. Now I wrote that for the first 5 on my diagram. Then what you're going to do, you're going to place an arrow up. Now what does the arrow represent? Naomi? Right, it's like clockwise or counterclockwise. Now I would call the up one clockwise and the down one counterclockwise. Remember, the electrons are traveling in circular origins around the nucleus. They're following that origin around the nucleus. They're not going like all over the place because they would be very difficult to predict. They'd start running into each other, stability would be a problem, and then we would not have 82 stable isotopes. The electrons help the atom become stable.
So does this help us figure out what this is?
Yes. So if you remember from nuclear chemistry, a beta particle can come in and affect the nucleus. And what is a beta particle?
Oh, that's E over.
It's an electron. So electrons can come in outside and hit the nucleus. Those electrons would not be traveling in circular origins. Those would probably be following a direct line. How can they form that way? Well, if you look at nuclear decay, they produce those beta particles. The sun produces beta particles in nuclear reactions. So chemical reactions don't typically produce beta particles. Nuclear ones do. All right, so Andrew asked a really good question. He was asking about whether beta particles from the sun make it to us. They do not. They're too big, and they travel probably not fast enough to make it to the Earth. So beta particles not going to make it to the Earth. Now gamma, now some ions can. They've talked about when the sun has a storm and they group together. So in that sense, they might be able to make it as a group. And if you ever heard about that, there was like a solar storm back in the 1800s that caused some telephone poles to ignite, catch on fire because of the wires. So that would be a case where that might be possible. We're only going to do 12, and then we're going to talk about these 12 when they gain and lose electrons. Seek out and find that. So fluorine would be an element that has a desire for change. Reactions don't occur unless there's a desire. So fluorine's going out there, it sees a metal. So let's take a look at this metal here, magnesium. How many protons does magnesium have? How many protons does magnesium have?
12.
12.
So we got 12 protons and how many neutrons?
12. I mean,
12.
Is it 12?
Yeah.
Now we have electrons in place. 1, 2, right? 3, 4, 5, 6, 7, 8, 9, 10. 8 and 2 is 10, right? And our next energy level, we're going to have 1, 2. Is everybody clear? So magnesium, if you look up here, it has 2 radicals. It has 2 electrons that it wants to lose. So how many fluorines would it take to get those 2 electrons? Yeah, so you would end up getting something like this, MgF2. That's kind of a little bit down the road for us, but that's how formulas are formed. Now, when magnesium loses those 2, it's going to behave like the noble gas underneath of it, neon. So magnesium wants to be like neon, which is nice. And then fluorine's going to behave like neon. They're both going to be behaving like neon because of the 8. That's the goal, is to be stable. Now, these things, the goal of this is to get these where they're stable. Did I show you the lights yesterday from the nanotechnology?
That's wrong.
That's right. I got it right here.
I'm serious. I'm living there. You took my shit.
Have to look so far.
No.
What's missing?
Gonna come up here and help him.
Couldn't come help me, bro. I think I'm close. Should these be S?
I don't know. Koenig, help him.
Is it supposed to be in order or not?
Yes, in order. Hydrogen, helium, lithium. We're not doing these. We're in the first 6 on the periodic table.
Yeah.
That is correct. Nice job. Yeah.
Oxygen.
I think they're talking about the
Alright, so it's only gonna change. So I'm just gonna keep this, but I'm gonna change.
It's gonna. This is gonna go to 3.
3. Yeah, that's what I
Then
was.
4. Okay.
Is it for real?
Mrs. Daddy could get into it.
That's right.
No.
2p4 is right.
You sure?
Yes. Because that's 2p5. 1 shape. That's a 1. How many shapes are in the P?
1.
No. Raise your hand. Alex? There are 3 shapes in the P.
Oh.
Or how many shapes are in the D? Koenig?
5.
5. How many shapes are in the F? Koenig? 7. She's writing down the next 4 on the periodic table. So what she's doing, she's recording like what I'm asking you to right here. So we started with hydrogen, first element. These are the first 10 elements in the periodic table.
Configuration. By the other rows. Those electron configuration.